There is a hole in the sky. Not a hole you could point a telescope at and see with your own eyes, but something stranger. Something that shows up only when you know how to read the faint microwave hiss filling every direction of the sky at once. It exists in the oldest light in the universe, a faint microwave glow that fills every corner of the sky, left over from a time before stars, before galaxies, before atoms had even finished forming. Astronomers call it the cosmic microwave background, the faint relic glow of creation itself, and across nearly the entire sky it is almost perfectly uniform. Almost. In the constellation Eridanus, there is a patch of sky where that ancient light runs colder than it should. A discrepancy so unusual that 2 decades after its discovery, scientists still argue about what it means. Some call it a statistical accident. Others call it the fingerprint of the largest empty region ever mapped. And a small, serious group of physicists have asked a far stranger, far more provocative question, one most of their colleagues remain openly skeptical of. Could this cold patch be a bruise? A scar left behind from the moment our universe brushed against another one? Before we can understand why that idea is even taken seriously by working physicists, we need to understand what we are actually looking at when we look at the cosmic microwave background. Because almost nothing about it is intuitive. And the story of how we found it is almost as strange as the anomaly itself. In 1964, 2 radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, trying to use an unusually sensitive horn antenna, originally built for satellite communication, to study radio emissions from our own galaxy. No matter where they pointed the antenna, they kept picking up a faint, steady hiss of microwave noise that would not go away. They checked every possible source of interference they could think of. They ruled out nearby New York City. They ruled out military radar. They famously climbed inside the antenna and cleaned out what they described as a white dielectric material, which turned out to be pigeon droppings. And still the signal persisted, uniform in every direction, day and night, in every season. What they had stumbled onto, without initially realizing it, was the afterglow of the Big Bang itself, a prediction made years earlier by physicists Ralph Alpha and Robert Herman, and independently pursued at the time by a team at Princeton led by Robert Dick, who had been actively building an instrument to search for exactly this signal when Penzias and Wilson beat them to it by accident. The 2 discoveries were published together in 1965, and the cosmic microwave background went, almost overnight, from a theoretical prediction to a measured fact of nature. Penzias and Wilson received the Nobel Prize in Physics in 1978 for a discovery they had not initially set out to make. Roughly 13,800 million years ago, the universe was not a place you could stand in. It was an unimaginably hot, dense plasma, a fog of particles slamming into each other so violently that light itself could not travel more than a short distance before being scattered again. For the first 380,000 years of cosmic history, the universe was opaque, the way the inside of a thundercloud is opaque. Then, as the universe expanded and cooled, something changed. The plasma cooled enough for electrons to bind to protons and form neutral hydrogen atoms, an event cosmologists call recombination, somewhat confusingly, since the electrons and protons were combining for the first time rather than recombining. In that instant, the fog lifted. Photons that had been trapped, bouncing endlessly off charged particles, were suddenly free to travel in straight lines. That burst of light, released in every direction across the newborn universe, is still traveling today. We call it the cosmic microwave background, and it is, in a very real sense, a photograph of the universe at the moment it became transparent, sometimes called the surface of last scattering. The furthest back in time any telescope built to detect light can ever, even in principle, see? Because that light has been stretching along with the expanding universe for nearly 14 billion years. It has cooled from a blistering few thousand degrees down to a whisper, about 2.7 degrees above absolute zero. It no longer appears as visible light. It shows up in microwaves, which is why the instruments built to study it are radio telescopes and satellites, rather than optical observatories. For nearly 2 decades after its discovery, the cosmic microwave background appeared to be perfectly smooth, a uniform 2.7 degrees in every direction. to the limits of what ground-based instruments could measure. That smoothness was itself a puzzle. If the early universe had been perfectly uniform in temperature, there would have been nothing for gravity to grab onto, no denser regions to collapse into galaxies, no way to build the lumpy, structured universe we actually observe today, full of stars and galaxies and vast empty voids between them. Theorists were confident tiny variations had to be there, seeds of structure imprinted at the earliest moments of cosmic history. But for years, no instrument was sensitive enough to detect them. That changed in 1992, when NASA's Cosmic Background Explorer satellite, led by George Smoot and John Mather, announced the first detection of these fluctuations, tiny temperature variations of only about 1 part in 100,000, rippling across the microwave sky. Smoot famously described the pattern at a press conference that made front-page news around the world as looking at the face of God, a characterization many of his fellow scientists gently pushed back on as more poetic than precise. But the underlying discovery was undeniably profound. Smoot and Mather shared the Nobel Prize in Physics in 2006 for the discovery, and it confirmed for the first time that the blueprint for all future cosmic structure really was written into the earliest light in the universe. Almost all of those temperature fluctuations, the ones Smoot and Mather first detected, are small, gentle, and statistically unremarkable. Exactly what you would expect from a very specific and well-tested theory called cosmic inflation. To understand why inflation was proposed at all, it helps to understand the problems it was built to solve. Because the theory did not arise from idle speculation. It arose because, without it, several basic features of our universe made no sense. The first was called the horizon problem. If you look at the cosmic microwave background in one direction of the sky, and then in the exact opposite direction, you are looking at regions of space that, according to standard Big Bang expansion without inflation, would never have had time to exchange so much as a single photon of light with each other since the beginning of the universe, because light itself has not had enough time to cross the distance between them. And yet both regions have almost exactly the same temperature, to a precision of about 1 part in 100,000. How can two regions of the universe that have never been in causal contact with each other agree so precisely on their temperature? It is a little like finding two students in opposite corners of a stadium, who have never spoken to each other and never seen each other's papers, turning in identical answers to an exam. The second was called the flatness problem. The overall geometry of the universe, whether space curves back on itself like the surface of a sphere, curves outward like a saddle, or is perfectly flat, depends on the total density of matter and energy compared to a specific critical value. Observations show the universe today is flat or extraordinarily close to it, to within a very small margin of error. The trouble is that running the equations of general relativity backward in time without inflation, any tiny deviation from perfect flatness in the early universe should have been dramatically amplified over billions of years of expansion, not smoothed out. For the universe to look this flat today, without inflation, the early universe would have needed to be flat to an almost unbelievable, seemingly implausible degree of precision, described by physicists as an extreme fine-tuning problem in its own right. The third was called the monopole problem, related to predictions from certain particle physics theories that the extremely early universe should have produced large numbers of exotic, extremely heavy particles called magnetic monopolies, objects with only a north or only a south magnetic pole, unlike every magnet ever observed in a laboratory, which always has both. These predicted particles have never been detected, despite dedicated searches, and standard Big Bang cosmology without inflation offered no good explanation for their apparent absence. In 1981, the physicist Alan Guth, then working at the Stanford Linear Accelerator Center, proposed a strikingly simple solution to all three problems at once. If, in an infinitesimal fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid period of exponential expansion, stretching space by an almost incomprehensible factor, all three problems would be resolved together. The horizon problem disappears because the entire observable universe today would have originated from a tiny patch of space, small enough to have been in close causal contact before inflation stretched it apart, explaining the uniform temperature. The flatness problem disappears because inflation would have stretched out any initial curvature so dramatically that the universe would appear flat afterward. The same way the surface of a balloon looks locally flat if you blow it up to an enormous size. And the monopole problem disappears because any monopoles produced before or during the very earliest moments would have been diluted to an undetectably low density by the same dramatic expansion. Guth's original model had technical problems of its own, difficulties smoothly ending the inflationary period, which was substantially resolved through what became known as new inflation, developed independently and nearly simultaneously by André Linde in the Soviet Union and by Andreas Albrecht and Paul Steinhardt in the United States in 1982. Linde went on to develop an even more influential variant called chaotic inflation in 1983, which proposed a simpler, more generic starting mechanism, and which forms much of the basis for the modern picture of eternal inflation we will return to later in this story. Crucially, inflation was not simply a clever mathematical patch invented to solve these three problems and nothing else. It made a further testable prediction. If inflation stretched microscopic quantum fluctuations, the same kind of tiny, inherent randomness that governs the behavior of subatomic particles, up to macroscopic, eventually cosmic scales, those fluctuations should have left a specific statistical fingerprint in the density of the early universe. A fingerprint that should be visible today as the pattern of temperature fluctuations in the cosmic microwave background. Specifically, inflation predicted these fluctuations should be nearly, though not perfectly, scale invariant, meaning fluctuations of different physical sizes should appear with almost, but not exactly, the same statistical strength. And it predicted they should be very close to Gaussian, statistically random in the same well-behaved, bell curve sense that many natural phenomena are random, without unusual, sharply defined features. When the Wilkinson microwave anisotropy probe launched in 2001, and later the European Space Agency's Planck satellite, launched in 2009, mapped the cosmic microwave background with far greater precision than the original cosmic background explorer, they confirmed these predictions to remarkable accuracy, which is a major reason inflation is considered one of the best supported ideas in modern cosmology, even though the specific physical mechanism, the identity of whatever quantum field actually drove that early exponential expansion, sometimes generically called the inflaton field, remains unidentified and an area of active theoretical work. It is against this backdrop of extraordinary success, a theory that solved three separate long-standing puzzles and then made a further prediction later, confirmed with exquisite precision, that any deviation from what inflation predicts becomes scientifically significant. And the cosmic microwave background, even in its broad strokes, was never perfectly, flawlessly uniform in the way the simplest inflationary picture might suggest. Long before the cold spot became famous, cosmologists studying the earliest full-sky maps noticed a handful of other puzzling, large-scale features, subtler than the cold spot, but part of the same broader pattern of anomalies, worth understanding because they show that the cold spot did not appear in isolation. One is called the low quadrupole anomaly, referring to the observation that the largest scale pattern of fluctuations in the cosmic microwave background, technically described using a mathematical tool called spherical harmonics, appears somewhat weaker than the simplest inflationary models predict. First noticed in the original Cosmic Background Explorer data and confirmed by both the Wilkinson Microwave Anisotropy Probe and Planck. Another is sometimes called the axis of evil, a slightly tongue-in-cheek name coined by cosmologist João Magejo and collaborator Kate Land in 2005, referring to an unexpected alignment between several of the larger-scale patterns in the cosmic microwave background and the geometric plane of our own solar system. An alignment that, if it reflects anything physically real rather than coincidence or a subtle, still unidentified systematic error in how the data is processed, would be deeply strange, since there is no known reason the earliest light in the universe should care about the orientation of our comparatively tiny, comparatively recent solar system. A third is called the hemispherical power asymmetry, the observation that temperature fluctuations appear to have slightly, statistically significantly, more power, more variation in one half of the sky than the other, an asymmetry confirmed independently by both the Wilkinson microwave anisotropy probe and Planck, and which some theorists have suggested could, like the cold spot, hint at physics beyond the very simplest inflationary models, though, like the cold spot, it remains unresolved and its ultimate cause is unconfirmed. None of these anomalies, on their own, is considered overwhelming evidence against standard cosmology. Individually, each has a statistical significance in a similar range to the cold spot, tantalizing but well short of the threshold physicists require to call something a confirmed discovery. But taken together, they form a pattern that keeps a healthy, active subfield of cosmology focused on so-called large-angle anomalies, testing whether standard inflationary cosmology is complete, or whether it is missing something at the very largest observable scales. The cold spot is, in many ways, the most famous and most intensively studied member of this family of puzzles. Not because it is definitively the strangest, but because its potential explanations, ranging from an enormous ordinary void to a literal collision between universes, span an unusually dramatic range, from the mundane to the almost unbelievable. Between the cosmic background, explorers' initial detection of fluctuations in 1992, and the launch of the Wilkinson microwave anisotropy probe in 2001, a series of high-altitude balloon experiments filled an important gap, flying instruments to the edge of the atmosphere, above most of the water vapor that interferes with microwave observations from the ground, without the enormous cost of a full satellite mission. The most influential of these was called Boomerang, short for Balloon Observations of Millimetric Extragalactic Radiation and Geophysics, which circled above Antarctica in late 1998, carried by the polar vortex winds and returned data precise enough to measure, for the first time with real statistical confidence, the characteristic angular size of the largest hot and cold spots in the cosmic microwave background, a measurement that translates directly into a measurement of the overall geometry of the universe. Along with a similar experiment called Maxima, the Boomerang results, published in 2000, provided strong evidence that the universe is very close to spatially flat, a striking early confirmation of one of inflation's central predictions, achieved several years before the Wilkinson microwave anisotropy probe would confirm and refine the same result with far greater precision. The Wilkinson microwave anisotropy probe itself, launched in June of 2001 and named after cosmologist David Wilkinson, one of the pioneers of cosmic microwave background research, who died shortly before the mission returned its first results, was deliberately placed not in orbit around Earth, but much further out, at a gravitationally stable location called the second Lagrange point, roughly 1.5 million kilometers from Earth in the direction away from the Sun, chosen specifically because it allowed the spacecraft to keep the Earth, Sun and Moon all consistently behind a protective shield, giving its sensitive microwave detectors an unobstructed, thermally stable view of deep space. The mission returned data for 9 years before being retired, refining our knowledge of the universe's age, composition, and geometry with each successive data release. Its successor, the European Space Agency's Planck satellite, launched in May of 2009 and placed at the very same gravitationally stable location, carried 2 complementary sets of detectors, a low-frequency instrument and a high-frequency instrument, together covering a much broader range of microwave frequencies than the Wilkinson microwave anisotropy probe, cooled to within a fraction of a degree of absolute zero using a multi-stage refrigeration system, allowing it to measure the cosmic microwave background with roughly 3 times the sensitivity and considerably sharper angular resolution, which is precisely the improvement in data quality that allowed researchers, in the years that followed, to test the cold spot's proposed explanations with far greater statistical rigor than the original Wilkinson microwave anisotropy probe data alone could support. In 2004, a team led by the astronomer Pablo Vielva was combing through the first-year data from the Wilkinson microwave anisotropy probe using a mathematical technique called a wavelet transform, essentially a way of examining the sky at many different resolutions simultaneously, using mathematical functions called spherical Mexican hat wavelets to hunt for statistically unusual features that a simpler, single-resolution analysis might miss entirely. In the direction of the constellation Eridanus in the southern sky, they found something that did not fit. a large region spanning roughly 10 degrees of sky, about 20 times the angular width of the full moon, where the temperature of the cosmic microwave background ran colder than anywhere else on the map. Follow-up analysis by Marcos Cruz and colleagues, published over the following several years, confirmed and characterized the feature further, testing it against a variety of statistical measures, including a measurement called kurtosis, which quantifies how much a distribution deviates from an ordinary Gaussian bell curve shape, particularly in its tails, its most extreme values. It became known without much ceremony as the cold spot. At first glance, 10 degrees of sky and a temperature dip of a few dozen microkelvin might not sound like the makings of a cosmic mystery, but the numbers behind it are what make it strange. Later work estimated that if this cold region corresponds to an actual underdense region of space, a void, it could span something on the order of 1.8 billion light-years across, one of the largest coherent structures ever proposed in the observable universe. To put that in perspective, our entire Milky Way galaxy is about 100,000 light-years across. The distance from us to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. A structure a billion light-years wide is not just large. It strains our understanding of how structure is supposed to form in a universe that inflation predicts should be, on the largest scales, close to uniform. This is the point where the story really begins, because a large cold spot on a mostly uniform ancient photograph should not exist under the simplest, most successful cosmological model we have, often called the standard lambda cold dark matter model, where lambda refers to the cosmological constant, the simplest mathematical description of dark energy, and cold dark matter refers to the mysterious, non-luminous form of matter that outweighs ordinary matter roughly 5-to-1 across the universe and provides the gravitational scaffolding around which galaxies form. The evidence for this invisible component of the universe is itself worth a brief mention, since it forms an essential part of the same broader picture the cold spot sits within. Suspicion that something unseen might be adding extra gravity to the cosmos dates back to 1933, when the astronomer Fritz Zwicky, studying the motions of galaxies within the Coma galaxy cluster, found they were moving far too quickly to be held together by the gravity of the visible matter alone, unless the cluster contained far more mass than could be directly observed. Mass he termed Dunkel Materie, German for dark matter. The idea gained much broader acceptance decades later, through the painstaking work of astronomer Vera Rubin and collaborator Kent Ford in the 1970s, who measured the rotation speeds of stars at different distances from the centers of spiral galaxies, and found that stars far from a galaxy's visible center were orbiting just as fast as stars much closer in, a pattern flatly inconsistent with the distribution of visible matter alone, and explainable only if each galaxy were embedded within a much larger invisible halo of additional mass. Further, independent confirmation came from gravitational lensing, an effect predicted by Einstein's general theory of relativity, in which the gravity of a massive foreground object bends and distorts the light of more distant background objects passing near it, allowing astronomers to directly map the total distribution of mass in a galaxy cluster, including whatever invisible matter it contains, regardless of whether that matter emits any light at all. Perhaps the most visually striking confirmation came in 2006, from observations of a system called the Bullet Cluster, the aftermath of a collision between two galaxy clusters, in which X-ray observations revealed that the hot, visible gas from the two clusters, which makes up most of their ordinary luminous matter, had collided and slowed dramatically, while gravitational lensing maps showed that most of the mass in the system had passed straight through the collision, largely undisturbed, exactly as expected if that mass consisted of dark matter particles that interact with each other, and with ordinary matter only through gravity, rarely or never through the same electromagnetic and nuclear forces that slow down and heat ordinary gas. Despite this overwhelming, multiply-independent observational evidence that dark matter exists in some form, its fundamental particle nature remains unidentified, one of the most significant open questions in physics, with leading theoretical candidates, including weakly interacting massive particles and axions, both actively searched for in dedicated underground and laboratory experiments around the world, so far without a confirmed detection. That model, built on decades of observation and refined again and again against new data, describes a universe where structure grows gradually and statistically predictably from those tiny inflationary seeds. A void a billion light-years across, sculpting a detectable cold imprint in the very oldest light in the universe, is not something that model comfortably explains. So scientists had to ask the obvious question first, before reaching for anything exotic. Is this real or is it an illusion? If you want to stick with us through what turns out to be one of the more genuinely unresolved puzzles in modern cosmology, now is a good moment to hit subscribe, because we are about to walk through exactly how physicists tried, and largely failed, to explain this anomaly away using ordinary physics, before turning to the far stranger possibilities that remain on the table. It is worth pointing out, before moving on, that the cold spot was not found by anyone specifically hunting for evidence of other universes. Vielva and his colleagues were running a general-purpose statistical search across the entire sky, looking for any region that departed unusually strongly from the expected Gaussian pattern, without any particular hypothesis in mind about what such a region, if found, might mean. That detail matters for how we should think about everything that follows. The exotic explanations came afterward, proposed by theorists trying to account for a genuine, already established anomaly in the data, not proposed first and then conveniently confirmed by a search designed to find them. Good science tends to work in that order: observation first, explanation second. And the cold spot's origin story follows that order cleanly, even if some of the explanations eventually proposed for it turned out to be considerably stranger than anyone initially expected. The first suspect in any anomaly like this is always the instrument and the analysis, not the universe. Scientists are deeply, almost reflexively skeptical of their own results, and rightly so, because the history of astronomy is littered with anomalies that turned out to be equipment artifacts, calibration errors, or statistical illusions. So the cold spot was hunted for mundane explanations first. One early candidate was foreground contamination. The cosmic microwave background does not arrive at our detectors in pristine form. Between us and that ancient light lies our own galaxy, full of dust and gas that emit and absorb microwave radiation at specific, well-characterized frequencies, along with more distant galaxy clusters and other structures that can subtly distort the signal through their own gravity or their own emitted radiation. Cosmologists have to carefully subtract all of this foreground noise. Using observations made it multiple different microwave frequencies, since foreground contamination and the true primordial signal behave differently across the electromagnetic spectrum to isolate the true cosmological pattern. Could the cold spot simply be a mistake in that subtraction? Dust in our own galactic backyard, masquerading as a cosmological feature? Researchers checked this carefully, comparing multiple foreground removal techniques, including methods with names like the internal linear combination method and needlet-based component separation, and comparing results across multiple independent datasets, including both the Wilkinson microwave anisotropy probe and the later, more sensitive Planck satellite, which used different instruments, different frequency bands, and different systematic errors. The cold spot showed up in both, essentially unchanged. Whatever it was not a foreground artifact specific to one telescope or one cleaning method. The second and more stubborn candidate was that this was simply a statistical fluke, an unlikely but not impossible feature of a random field. This is a subtler point than it sounds, and it is worth taking seriously, because in a genuinely random pattern, spanning the entire sky, you expect a few unusually cold or unusually hot patches purely by chance. The same way, if you flip a coin 10,000 times, you will occasionally get a run of 10 heads in a row without anything being wrong with the coin. The question researchers had to answer was not simply, is this patch cold? But how cold is it compared to what we would expect from pure random chance? Given the number of places on the sky we could have looked, a subtlety known as the look elsewhere effect, a statistical trap that has fooled scientists in other fields too, most famously discussed in particle physics during the search for the Higgs boson, where researchers had to be extremely careful not to mistake random statistical bumps in their data for a genuine new particle. To understand what a statistical significance of 2 or 3 standard deviations actually means in plain language, it helps to picture a bell curve. the familiar bell-shaped distribution that describes how many natural quantities, human height, measurement errors, and, in this case, random temperature fluctuations in a mostly uniform field tend to cluster. Most values fall close to the average, with progressively fewer and fewer values as you move further out toward the extremes in either direction. A result at one standard deviation, often written as 1 sigma, from the average is common, happening by chance more than 30 times out of 100 trials. A result at 2 standard deviations is less common, happening by chance only about 5 times out of 100 trials. A result at 3 standard deviations is genuinely unusual, happening only about 3 times out of 1,000 trials. Physicists have generally settled on a much stricter standard before calling something a confirmed discovery. 5 standard deviations, corresponding to odds of roughly 1 chance in 3.5 million of the result occurring purely by chance. A threshold that has served the field well, having prevented numerous false discoveries from being prematurely announced over the decades, though it has also occasionally meant that genuinely real but subtle effects took years, or even decades longer to confirm than enthusiasts might have liked. Early estimates suggested the cold spot was unlikely at roughly the 1 in 100 to 1 in 1,000 level, once you accounted for the look elsewhere effect, translating to a statistical significance of around 2 to 3 standard deviations. In physics, that is a meaningful anomaly worth investigating, but it is nowhere near the 5 sigma threshold required for a genuine discovery. In plain terms, the honest scientific answer, even today, is that we cannot completely rule out the possibility that the cold spot is simply an unusually large, but ultimately unremarkable fluctuation, the kind of thing that a big enough random universe eventually produces somewhere, purely by chance. It is worth remembering, too, that the observable universe contains an almost unimaginable number of possible 10-degree patches of sky, and finding one unusually cold patch somewhere among all of them is a rather different statistical claim than predicting in advance that a specific patch would be unusually cold and then finding exactly that. It is also worth noting that statisticians and cosmologists have continued refining exactly how to calculate the cold spot's true significance in the years since its initial discovery, and the debate over the precise number has itself become a small technical subfield of its own. Different research groups, using different statistical estimators, different assumptions about the underlying shape of the anomaly, and different treatments of the look elsewhere effect, have published significance estimates ranging from roughly 1 in 50 to considerably rarer than 1 in 1,000, a range wide enough that reasonable, careful scientists continue to disagree about exactly how surprising the cold spot really is, even while agreeing on the underlying data itself. This kind of persistent technical disagreement is not a sign that something is wrong with the science. It is closer to the opposite, a sign that researchers are being appropriately careful about a genuinely subtle statistical question, rather than rushing to declare either that the anomaly is nothing at all, or that it is definitively, unambiguously real. That admission matters, and any honest account of this story has to include it clearly, because it is the foundation everything else is built on. But a 2 to 3 sigma anomaly is also not nothing. It is exactly the kind of tantalizing, unresolved signal that drives scientists to dig deeper, rather than shrug and move on. And digging deeper is exactly what happened next, when attention turned away from statistics and toward astronomy, toward the actual patch of sky the cold spot occupies. If the cold spot were not simply a random fluctuation baked into the primordial light itself, there was another, more physical possibility. Perhaps something happened to that ancient light on its long journey to us, something in the foreground universe, much closer to home than the era of recombination, that subtly cooled it as it passed through. This brings us to one of the more elegant pieces of physics in this entire story, called the integrated Sachs-Wolfe effect, first described by Rainer Sachs and Arthur Wolfe in 1967 and later extended, in the specific form relevant here, by Martin Rees and Dennis Schema. Here is the basic idea. As a photon from the cosmic microwave background travels across billions of light-years of space, it does not travel through a perfect vacuum. It passes through regions of the universe that are denser than average, like galaxy clusters, and regions that are emptier than average, called voids. When a photon falls into the gravitational well of a dense region, it gains energy, and when it later climbs back out, in a universe where the expansion of space is constant, it loses exactly that same amount of energy, and the two effects cancel out perfectly, leaving the photon unchanged. But our universe is not static. It is expanding, and in the present cosmic era, that expansion is accelerating, driven by whatever mysterious component of the universe we call dark energy. Understanding why physicists are so confident about that acceleration is worth a brief detour of its own, because it is one of the most important cosmological discoveries of the last several decades. In the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were using a particular class of exploding stars called Type Ia supernovae as what astronomers term standard candles, objects whose intrinsic brightness is well understood, meaning their apparent brightness, as seen from Earth, reveals their precise distance. Both teams set out expecting to measure how much the expansion of the universe was slowing down over cosmic history, since gravity, pulling all that matter together, should have been acting as a brake on cosmic expansion. Instead, both teams found, independently and to their own initial surprise and skepticism, that distant supernovae appeared dimmer, meaning further away, than they should have been if the expansion were merely coasting or slowing. The only explanation that fit the data was that cosmic expansion was not slowing down at all, but speeding up. A discovery so unexpected that both teams spent months trying to find the error in their own analysis before finally, cautiously, announcing the result in 1998. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for the discovery. Whatever is driving that acceleration, we call dark energy, and it now appears to make up roughly 68% of the total energy content of the universe, dwarfing both ordinary matter and dark matter combined, despite the fact that we still do not know, at a fundamental physical level, what it actually is. That acceleration breaks the perfect symmetry between falling into and climbing out of a gravitational well. If a photon falls into a gravitational well while the universe is still expanding and that well is, in a sense, shallower by the time the photon climbs back out, because the surrounding matter has thinned out further due to accelerating expansion, the photon exits with slightly more energy than it entered with, gaining a small blue shift as it passes through a dense supercluster. The reverse happens for a void. A photon traveling through an enormous underdense region loses a small amount of energy passing through, and does not fully regain it as it exits, because the void has become relatively even emptier by the time the photon leaves. The net result is a slight cooling, a redshift, a slight loss of energy for voids, and a slight warming, a blue shift, for superclusters. This is the integrated Sachs-Wolfe effect, and it has been measured on average by stacking the cosmic microwave background signal from many known superclusters and supervoids identified in galaxy surveys, in influential work led by Benjamin Granet, Mark Neerink, and Istvan Sapudi in 2008, confirming statistically, across the full sample, that dark energy really is reshaping the cosmic microwave background as light crosses the more recent universe on its way to us, even though the effect from any single void or cluster is generally far too small to detect on its own. Could an enormous void sitting between us and the surface of last scattering in the direction of Eridanus explain the cold spot through exactly this mechanism? It was an appealing idea because it did not require any new physics at all, only a very large, very empty region of ordinary space. Astronomers went looking. In 2015, using data from the Wide Field Infrared Survey Explorer and the Pan-STARRS survey, a team led by physicist Istvan Sapudi announced they had found exactly that, a genuine supervoid in the direction of the cold spot, sitting at a distance corresponding to roughly 3 billion light-years away, with an estimated diameter in the range of 1.8 billion light-years, making it, at the time, one of the largest voids ever identified, sparse enough in galaxies to plausibly explain at least part of the temperature deficit through the integrated Sachs-Wolfe effect. This finding made headlines around the world, and for a while it looked like the mystery might be solved through nothing stranger than an extraordinarily large, extraordinarily empty region of ordinary cosmic geography, now sometimes referred to as the Eridanus Supervoid. But the story did not end there, and this is the part that keeps the mystery alive rather than closing it. Follow-up analyses, including detailed work using galaxy survey data from the Dark Energy Survey, published by a team led by Anna Kovas in 2017 and refined in subsequent years, confirmed that there is indeed an underdense region along that line of sight, but found that its measured depth and size, while real, appeared insufficient using standard cosmological models to produce a temperature dip in the cosmic microwave background as large as the one actually observed. Some studies estimated the void could account for perhaps 10 to 20% of the cold spot's depth through the standard linear integrated Sachs-Wolfe effect, leaving the rest unexplained by that mechanism alone. Other researchers proposed that a stronger, non-linear version of the same physics, called the Rees-Siama effect, which becomes more significant for very large, very deep voids evolving under gravity in a non-linear way, as matter continues to flow outward from the void's center over cosmic time, might close some of that gap. Though this remains actively debated, and calculations have produced a range of different answers, depending on the specific assumptions used about the void's exact shape, depth, and evolutionary history. Some more recent statistical reanalyses have gone even further, questioning whether the supervoid identified by galaxy surveys is quite as anomalously large or empty as first reported, once you account for the same look elsewhere effect that complicated interpretation of the cold spot itself. Since astronomers were, in a sense, specifically looking for an unusual void in exactly the region where an unusual cold spot had already been found, a search strategy that can itself introduce statistical bias if not handled with great care. To appreciate just how unusual a void of this proposed scale would be, it helps to know a little about the broader history of mapping cosmic voids in general, because the Eridanus Supervoid would not be the first enormous, sparsely populated region of space astronomers have found, though it might be one of the largest. The very existence of voids as a distinct category of cosmic structure was itself a surprise. Through the middle of the 20th century, most astronomers pictured galaxies as scattered through space in a roughly uniform, if clumpy, distribution without any expectation of the vast, genuinely empty regions we now know exist. That picture changed decisively in 1978, when astronomers Stephen Gregory and Laird Thompson, studying the distribution of galaxies in and around the constellation Coma, identified a large, startlingly empty region nearly devoid of galaxies. A discovery followed in 1981 by Robert Kirshner, August Oehmler, Paul Schechter, and Stephen Schechtman, who identified an even more dramatic example while conducting a redshift survey, a technique that measures the distance to galaxies by how much their light has been stretched or redshifted by cosmic expansion. What they found in the direction of the constellation Albertus was a region roughly 250 million light-years across, containing only a small handful of galaxies, in stark contrast to the thousands that would typically occupy a volume of that size, a discovery that became known as the Boots Void, or sometimes with a certain amount of scientific humor, the Great Nothing. Its discovery, made using a survey covering only a small patch of sky, hinted that voids might be a common fundamental feature of cosmic structure rather than a rare anomaly, a suspicion that was decisively confirmed over the following decades as redshift surveys grew dramatically larger and more ambitious, culminating in projects like the Center for Astrophysics Redshift Survey in the 1980s, which first revealed that galaxies are not distributed randomly at all, but arranged in a vast, sponge-like cosmic web of filaments and clusters surrounding equally vast, largely empty voids, and later the 2-degree field Galaxy Redshift Survey and the Sloan Digital Sky Survey, beginning in the late 1990s and continuing for decades afterward, which mapped the three-dimensional positions of literally millions of galaxies, revealing this cosmic web structure in extraordinary, statistically rigorous detail across enormous volumes of the observable universe. Voids, once properly mapped this way, turned out to be genuinely enormous. Typical structures, not rare exceptions. Modern surveys have identified voids ranging from tens of millions to hundreds of millions of light-years across as an entirely routine feature of the universe's large-scale structure, occupying, by some estimates, well over half of the total volume of the observable universe, despite containing only a small fraction of its galaxies. Even more strikingly, in 2013, astronomer Amy Barger and collaborator Ryan Keenan identified what came to be called the KBC void, named for Keenan, Barger, and their colleague Lennox Cowie, an enormous underdense region roughly 2 billion light-years across that appears to contain our own Milky Way galaxy relatively near its center, a discovery that itself sparked considerable follow-up research into whether living inside such a large void could subtly bias certain other cosmological measurements, including, intriguingly, some of the same supernova distance measurements originally used to discover dark energy, a possibility that remains debated but has so far not overturned the standard picture of accelerating cosmic expansion. Against this broader backdrop, a proposed supervoid on the order of 1.8 billion light-years across, roughly comparable in scale to the KBC void, though at a much greater distance from us, is large but not entirely without precedent among the very biggest structures cosmologists have mapped. What makes the Eridanus Supervoid scientifically important is not simply its size, but the specific, quantitative question of whether a void of exactly that size, depth, and distance can produce a cosmic microwave background temperature dip as large as the one actually observed in the cold spot. A question that depends on detailed modeling of exactly how empty the void really is at every point within it, not simply its overall diameter. And it is precisely this detailed modeling that has proven difficult to fully reconcile with the observed depth of the anomaly. So where does that leave us? With a real supervoid genuinely mapped by galaxy surveys, sitting in exactly the right direction, but with an open question about whether ordinary physics operating on that void is enough, by itself, to fully account for the size and depth of the cold spot. This is the honest state of the field. It is not that scientists have ruled out mundane explanations and been forced into exotic ones. It is that the mundane explanations get us partway there, and a real, unresolved gap remains, one actively being investigated with newer, more sensitive galaxy surveys and updated statistical techniques as of the most recent analyses through 2026. It is precisely in that gap, that unresolved sliver of the puzzle, where the far stranger ideas enter the conversation, not as replacements for the supervoid explanation, but as proposals for what might be needed to close the remaining distance, or, in their most ambitious form, as competing explanations for the anomaly altogether. To understand why some physicists have proposed something as extraordinary as a collision between universes, we need to step back and ask a much bigger question first, one that sits at the heart of modern theoretical cosmology, entirely independent of the cold spot itself. Is our universe the only one there is? This question sounds like philosophy or science fiction, but it emerges directly and almost unavoidably from two of the most successful frameworks in modern physics: cosmic inflation and string theory, when you follow their mathematics to its logical conclusions. Remember inflation, the theory that solved the horizon, flatness, and monopole problems, and explains the statistical pattern of fluctuations we observe in the cosmic microwave background. Many of the leading mathematical models of inflation, when worked through carefully, do not naturally predict that inflation happens once and then simply stops everywhere at the same moment. Instead, in a class of models called eternal inflation, developed extensively by André Linde and others beginning in the mid-1980s, inflation ends locally in patches while continuing indefinitely elsewhere. Picture the fabric of space as a pot of boiling water. In most of the pot, bubbles occasionally form where the water has locally reached a lower energy state, and each bubble, once formed, stops boiling inside itself and settles into ordinary liquid, while the rest of the pot continues to boil around it, endlessly producing new bubbles. In this analogy, our entire observable universe, everything we can see with every telescope we have ever built, would be the inside of just one such bubble, one region where inflation ended and settled into the ordinary, slower expansion that produced stars, galaxies, and us, while the eternally inflating space beyond continues, unobserved, producing other bubbles, potentially with different physical properties, elsewhere. This is what physicists mean by the multiverse in this particular context. It is important to be precise here, because the word gets used loosely in popular science. This is not a claim about alternate versions of you making different life choices, the kind of multiverse popularized in comic books and movies. It is a mathematical consequence of taking the equations of eternal inflation seriously and following them to their logical conclusion, that if inflation happens the way the leading models suggest, it may be extremely difficult, perhaps even mathematically impossible within these models, for it to have happened just once, producing just one bubble. It is worth being precise about which kind of multiverse we are actually discussing, because physicists who study this topic seriously have found it useful to distinguish between several genuinely different concepts that all get lumped together under the same popular word. The cosmologist Max Tegmark proposed an influential classification scheme in 2003, sorting these ideas into 4 broad levels. A level 1 multiverse simply refers to regions of space so distant that their light has not yet had time to reach us, existing beyond our observable horizon, in an otherwise perfectly ordinary universe with the same physical laws as our own. A comparatively modest and almost uncontroversial idea, since it follows directly from an infinite, or merely very large, universe combined with a finite speed of light. A level 2 multiverse corresponds to the bubble universes produced by eternal inflation that we have been describing. Separate regions where inflation ended in different ways, potentially with different effective physical constants, though governed by the same fundamental underlying laws of physics from which they all emerged. A level 3 multiverse refers to something entirely different, an interpretation of quantum mechanics itself, first proposed by physicist Hugh Everett in 1957, sometimes called the many worlds interpretation, in which every possible outcome of a quantum measurement actually occurs, each in its own separately branching version of reality, an idea that remains one of several competing, unresolved interpretations of quantum mechanics rather than an established fact, alongside rival interpretations such as the Copenhagen interpretation and pilot wave theory. A level 4 multiverse, the most speculative of Tegmark's categories, proposes that every mathematically self-consistent structure corresponds to some physically real universe, an idea few working physicists treat as more than an interesting philosophical thought experiment. The specific multiverse relevant to the cold spot and the bubble collision hypothesis sits within Tegmark's level 2, and it is worth keeping that distinction in mind, because conflating it with the very different and separately controversial many worlds interpretation of quantum mechanics is a common source of confusion in popular discussions of this topic. String theory adds another layer to this picture, though it comes from a completely different direction, and its own history is worth understanding briefly, because it did not begin as a theory of everything at all. In the late 1960s, physicists including Gabriele Veneziano were originally trying to describe the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei, and stumbled onto mathematical structures that seemed to describe particles not as points, but as tiny vibrating strings. This early version of the theory was largely abandoned as a description of the strong force once a more successful theory, called quantum chromodynamics, came along in the 1970s. But a small number of physicists, including John Schwartz and Michael Green, continued developing the string framework through the 1970s and into the 1980s, discovering, somewhat to their own surprise, that it seemed to naturally require and incorporate a quantum description of gravity, something the standard model of particle physics has never successfully managed to do on its own. This realization, formalized in what is now called the first superstring revolution in 1984, transformed string theory from a somewhat obscure, largely abandoned idea about nuclear physics into one of the most actively pursued approaches to unifying all the fundamental forces of nature, including gravity, within a single mathematical framework. A second wave of major theoretical breakthroughs in the mid-1990s, sometimes called the second superstring revolution, led by physicists including Edward Witten, revealed deep mathematical connections between 5 previously distinct versions of string theory, suggesting they might all be different mathematical descriptions of a single, more fundamental underlying framework, sometimes called M-theory, though the full nature of that underlying framework remains even today, only partially understood. To make its mathematics internally consistent, string theory requires extra spatial dimensions beyond the 3 we experience. typically 6 or 7 additional dimensions, curled up at scales far too small for any experiment to have probed directly, an idea with roots going back even further, to a 1920s proposal by physicists Theodore Kaluza and Oscar Klein that a 5th dimension, curled up at a tiny scale, could unify gravity with electromagnetism. When physicists work through how these extra dimensions could be shaped and folded, called compactification, they find an enormous number of mathematically consistent possibilities. An estimate often cited is somewhere around 10 to the 500 power-distinct configurations, sometimes called the string landscape, developed extensively by Leonard Susskind and others in the early 2000s. Each configuration would correspond to a universe with potentially different fundamental constants, different particle masses, even a different number of effective dimensions experienced by observers within it. When you combine eternal inflation with the string landscape, you get a picture where each bubble universe produced by eternal inflation might settle into a different point in that landscape, a different configuration of physical law. It is worth being very clear that this remains a theoretical, mathematical framework, not an observationally confirmed reality. String theory itself has not been experimentally verified, despite decades of effort and enormous investment of theoretical talent, and some physicists, including notable critics like Peter Woit, author of a widely discussed 2006 book arguing string theory, had drifted away from testable physics, and Lee Smolin, who raised similar concerns the same year, have argued forcefully that the landscape idea risks becoming untestable and therefore not fully scientific in the traditional sense, since with such an enormous number of possible universes, almost anything could be said to be predicted somewhere within it. This tension connects to a much older and deeper debate in the philosophy of science, first articulated influentially by Karl Popper in the mid-20th century, who argued that a genuinely scientific theory must, in principle, be falsifiable, meaning it must make specific predictions that could, at least in principle, be shown wrong by some possible observation. Defenders of the string landscape, including Susskind, have pushed back, arguing the framework does make testable predictions, particularly regarding the statistical likelihood of certain physical constants, even if the underlying multiverse itself cannot be directly observed. This is a legitimate, ongoing, unresolved debate within theoretical physics, not a settled matter, and it is worth holding on to that tension as we continue. Within this landscape picture, cosmologists sometimes describe our observable universe using the language of brane cosmology, borrowed from string theory, where brane is short for membrane. In certain versions of string theory, particularly those explored by Lisa Randall and Raman Sundram in the late 1990s, ordinary matter and the forces we experience apart from gravity are confined to a lower dimensional surface, a brane embedded within a larger, higher dimensional space called the bulk. Gravity alone is thought to leak into that extra-dimensional bulk, an idea the Randall-Sundram model used to propose a novel explanation for why gravity appears so much weaker than the other fundamental forces, a long-standing puzzle in particle physics known as the hierarchy problem. This model gives rise to genuinely testable, if not yet confirmed, predictions in particle physics, some of which have been searched for, without success so far, at the Large Hadron Collider at CERN. And it also opens a striking possibility that other branes, other universes, could exist within that same higher dimensional bulk, potentially close to our own, potentially even moving relative to us within those extra dimensions. This brane framework produced one particularly important and directly relevant proposal worth pausing on, called the ekpyrotic universe, developed beginning in 2001 by Paul Steinhardt, Neil Turok, Justin Corey, and Bert Overoot. The name comes from an ancient Greek term referring to conflagration, fire, chosen deliberately because the model proposes that the Big Bang itself, rather than being a single, unique beginning of space and time, was the result of a literal collision between two three-dimensional branes moving through a higher dimensional bulk, an event so energetic it released the enormous heat and energy that we observe as the aftermath of the Big Bang. In its original and later, more developed cyclic form, this model proposes that our universe and a neighboring, parallel brane universe periodically collide, over cosmic timescales of trillions of years, with each collision triggering what looks, from the inside, like a new Big Bang, a genuinely alternative cosmological framework to standard inflation, one that attempts to explain the same observed features of the universe, its flatness, its uniformity, the pattern of its structure, through a fundamentally different mechanism. It remains a minority position within cosmology, and it faces its own significant theoretical challenges, including difficult, still not fully resolved questions about precisely what happens mathematically at the moment of brane collision itself. But it is a serious, peer-reviewed, actively studied proposal, and it demonstrates that the idea of universes literally colliding with one another is not a notion invented for popular science documentaries. It exists in a specific, technical, mathematically developed form within the actual research literature of theoretical cosmology. And this is where the idea at the center of our story emerges, an idea proposed and explored seriously, if speculatively, by a handful of theoretical physicists working primarily within eternal inflation rather than the ekpyrotic framework specifically, that if other bubble universes exist within an eternally inflating background, it is not obviously forbidden that two of them could, at some point in cosmic history, have brushed against each other, or even collided. The most serious and specific version of this idea, connecting bubble collisions directly to observable features in the cosmic microwave background, came from a research program developed largely in the 2000s by physicists, including Anthony Aguirre, Matthew Kleben, and Matthew Johnson. Their key insight was mathematically precise and worth explaining carefully because it is the actual scientific proposal, not a vague metaphor. If our bubble universe formed within an eternally inflating background alongside other bubbles, it is possible, under the right conditions, for two bubbles to collide before either has expanded so far that the space between them stretches faster than the collision could ever catch up. Since space itself is expanding and in an eternally inflating background, the space between bubbles is generally expanding extremely fast. If such a collision occurred early enough in our bubble's history, before this runaway expansion made further contact impossible, the disturbance would have propagated through our universe as a kind of shockwave. And if we happen to be positioned such that this shockwave passed through the region that later became the surface of last scattering, the source of the cosmic microwave background, it could, in principle, leave an imprint. Crucially, these researchers made a specific, falsifiable prediction about what that imprint should look like. A roughly circular or disc-shaped patch on the sky with a notably sharp, well-defined edge, distinct from the softer, more diffuse and irregular boundary that a supervoid or a random statistical fluctuation would typically produce, and with a particular predicted relationship between temperature and polarization patterns across that boundary, since a genuine bubble collision should imprint a distinctive pattern not just in temperature, but in the polarization of the microwave light itself, a separate, independently measurable property related to the specific orientation in which the light waves oscillate. This detail matters enormously for evaluating the honesty of the multiverse collision idea, because it means the hypothesis is not unfalsifiable science fiction. It makes a specific prediction that can be checked against real data, and it has been checked. Researchers including Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Piris carried out a dedicated search through the Wilkinson microwave anisotropy probe data in around 2011, using sophisticated Bayesian statistical methods designed specifically to search for the sharp-edged, disk-like signatures that bubble collisions were predicted to produce, methods that essentially compare, for every possible location and size on the sky, how much more probable the data would be if a genuine bubble collision signature were present there, against the alternative that the same region is explained entirely by ordinary statistical noise. Their initial analysis identified a small number of intriguing candidate regions, though the statistical significance was weak and the number of candidates was roughly consistent with what you might expect from noise alone once the enormous number of possible patches on the sky was properly accounted for. The same look elsewhere effect that complicated interpretation of the cold spot itself, when the far more sensitive Planck data became available, offering both better resolution and, critically, the polarization measurements that temperature data alone cannot provide, A similar search was carried out, and it did not find compelling evidence for the specific sharp-edged bubble collision signature anywhere on the sky, including, importantly, in the direction of the cold spot itself. The cold spot's boundary, in the highest resolution data available, appears more diffuse and irregular than the sharp edge the bubble collision models predict, which is a real strike against this particular hypothesis, and it deserves to be stated plainly rather than glossed over. This is a critical point, and one that responsible popular science coverage of this topic sometimes omits in the pursuit of a punchier story. The bubble collision hypothesis, in its most literal, most specific form, as tested directly against real data, has not found strong observational support, and in several respects, the data we do have seems to disfavor its cleanest predicted signature. So why does the idea persist at all in serious discussion rather than being fully discarded? Partly because the underlying theoretical motivation for a multiverse, arising independently from eternal inflation and the string landscape, and reinforced by the entirely separate ekpyrotic and cyclic brane collision models, remains a live and actively studied area of theoretical physics, regardless of what is or is not found in the cold spot specifically, and partly because a related but distinct proposal, put forward by the physicist Laura Mersini Houghton beginning in the mid-2000s, working with Richard Holman and others, took a different angle entirely, one rooted not in a literal spatial collision between expanding bubbles after the fact, but in something stranger from quantum mechanics called entanglement, present before inflation even began. To appreciate why Mersini Houghton's proposal is taken seriously despite sounding, at first, almost too strange to be real physics, it helps to understand what quantum entanglement actually is, since it is one of the most well-established, if genuinely counterintuitive, phenomena in modern physics, extensively confirmed in laboratory experiments here on Earth, long before any cosmological application was proposed. In quantum mechanics, two particles can become correlated in such a way that measuring a property of one particle instantaneously determines the corresponding property of the other, no matter how far apart they are, a phenomenon so strange that Albert Einstein, along with collaborators Boris Podolsky and Nathan Rosen, famously challenged it in a 1935 paper, arguing it implied either an impossible faster-than-light influence or that quantum mechanics must be an incomplete description of reality, missing some hidden underlying variables that would restore a more intuitive classical picture. This became known as the EPR paradox. In 1964, physicist John Stuart Bell devised a specific, testable mathematical inequality that any theory based on such local hidden variables would have to satisfy, providing, for the first time, a way to experimentally distinguish between Einstein's proposed resolution and the standard quantum mechanical prediction. Beginning with experiments by John Clauser and Stuart Friedman in the early 1970s, and refined dramatically over subsequent decades by physicists including Alain Aspect, and later by Anton Zeilinger and John Clauser again, whose combined work earned them a shared Nobel Prize in Physics in 2022 alongside Anton Zeilinger, these experiments have confirmed, with ever-increasing precision and with loopholes progressively closed, that quantum entanglement is real, that Einstein's hidden variable resolution does not hold, and that the strange, correlated behavior predicted by quantum mechanics genuinely occurs in nature, even though it does not actually allow information to be transmitted faster than light, since the specific outcome of any individual measurement remains fundamentally random. Mersini Houghton's proposal, developed within a framework sometimes called the string landscape multiverse, suggested that during the earliest moments before our universe's inflationary period, our region of space may have been quantum mechanically entangled with a neighboring universe, or neighboring universes, born from the same landscape, in a manner conceptually related to the entanglement confirmed in these laboratory experiments, though scaled up to a cosmological and highly theoretical context, far beyond anything directly tested. According to this proposal, the gravitational pull of that entangled neighboring universe could have left a subtle, specific gravitational imprint on our own universe's structure, one that, in her published predictions, should show up as an unusually cold, anomalously large region in the cosmic microwave background, along with a predicted deficit of galaxy clusters in the corresponding region of sky, since the entanglement would have subtly suppressed structure formation there. It is genuinely striking, and worth being honest about, that this specific prediction was published by Mersini Houghton and collaborators, including Rick Holman, before the depth and extent of the cold spot anomaly was as well characterized as it is today, and that a modest deficit of galaxy clusters in that same general direction has been reported in some subsequent galaxy survey work, including some of the same supervoid studies discussed earlier. Proponents of this idea point to that sequence as meaningful, a prediction made and later at least partially corroborated. Critics, and there are many serious ones within the physics community, point out that the theoretical framework underlying the prediction relies on aspects of string theory and multiverse cosmology that remain unconfirmed and, by some arguments, potentially untestable in principle, that the statistical significance of the cluster deficit is itself contested and has not been confirmed with high confidence by all subsequent surveys, and that a retrospective match between a broad theoretical prediction and a complex, still not fully explained, astronomical anomaly does not, on its own, constitute confirmation of anything as extraordinary as the existence of other universes. Some critics have further argued that the underlying quantum entanglement mechanism proposed to connect separate, causally disconnected universes rests on an extrapolation of quantum mechanics far beyond any regime where the theory has been tested, since ordinary quantum entanglement, as confirmed by Bell test experiments, involves particles that were once in contact or share a common origin, a very different situation from universes that, by definition, in most multiverse models, never share any causal connection at all. This is, honestly, about as far as the evidence currently takes us, and any documentary claiming otherwise would not be telling you the truth. We do not have proof of a collision with a parallel universe. What we have is a genuinely unresolved anomaly in the cosmic microwave background, a real, mapped supervoid that appears to explain part, but plausibly not all of it, through completely conventional physics, and a small set of serious, mathematically grounded but observationally, unconfirmed and in some respects disfavored proposals, suggesting the remainder might be explained by something as extraordinary as contact with another region of a larger multiverse. Those are three very different epistemic categories: an established observation, a partially successful conventional explanation, and a speculative, so far unconfirmed extension of theoretical physics. And keeping them clearly separated is the only honest way to tell this story. It is worth pausing here to address a question that naturally follows from everything we have just discussed. If a genuine multiverse does exist, arising from eternal inflation and the string landscape, what would that actually mean for how we understand our own universe? Beyond simply explaining one cold patch of ancient light, the most immediate and widely discussed implication concerns something cosmologists and philosophers of science call the fine-tuning problem. The strange observation that many of the fundamental constants of our universe, the strength of gravity, the mass of the electron, the precise value of the cosmological constant driving accelerating expansion, seem to sit within surprisingly narrow ranges that allow complex structures like stars, planets, and life to exist at all. Ranges that, if shifted by even a small percentage in either direction according to many calculations, would produce a universe without atoms, without chemistry, without anything resembling the world we know. The cosmological constant in particular presents one of the most extreme examples of this puzzle. Calculations from quantum field theory, estimating the energy density that should arise from the vacuum of empty space itself due to quantum fluctuations, predict a value for the cosmological constant that is larger than the value actually observed by a factor sometimes estimated as large as 10 followed by around 120 zeros. An almost incomprehensible discrepancy that physicist Steven Weinberg described in a highly influential 1987 paper as possibly the worst theoretical prediction in the history of physics, and one that led Weinberg himself to propose an early anthropic argument for why the constant might take the small value we observe. In a single universe picture, this apparent fine-tuning has struck many physicists and philosophers as demanding an explanation, whether through deeper physical law we simply have not discovered yet, some yet unknown symmetry or mechanism that naturally sets these constants to their observed values or otherwise. In a multiverse picture, it requires no special explanation at all, because if there are an enormous or even infinite number of universes, each with different physical constants scattered across the string landscape, it is entirely unsurprising that we, as observers capable of asking the question in the first place, would find ourselves in one of the comparatively rare universes where the constants happen to permit stars, chemistry, and life, an argument known as the anthropic principle, first articulated clearly by physicist Brandon Carter in 1973 and developed further in a highly influential 1986 book by John Barrow and Frank Tipler. This argument remains genuinely controversial within physics and philosophy of science. Serious critics, including physicist and Nobel laureate David Gross, among others, have argued it risks explaining everything and therefore predicting nothing, a concern that echoes the same testability worries raised about the string landscape more broadly, since an argument that can accommodate essentially any observed value of a physical constant by appealing to our own existence as observers provides comparatively little genuine scientific traction. And some critics worry it risks becoming a substitute for, rather than a spur toward deeper physical explanation. There is a further, stranger complication that arises within certain versions of the eternal inflation multiverse. Worth mentioning, honestly, even though it takes us slightly further from the cold spot itself, called the Boltzmann brane problem, named after the 19th century physicist Ludwig Boltzmann, who first raised a conceptually related puzzle about entropy and the origin of order in the universe. In an eternally inflating multiverse existing for an infinite or extraordinarily long span of time, some calculations suggest that random quantum fluctuations over sufficiently vast stretches of time could occasionally and spontaneously assemble a fully self-aware, conscious observer directly out of the surrounding vacuum, complete with false memories of a life never actually lived, without any need for stars, planets, or biological evolution at all. If the mathematics of a particular multiverse model implies that such spontaneously generated observers would vastly outnumber observers like us, who arose through the ordinary, comparatively much slower process of stellar and biological evolution, some physicists, including Alan Guth himself, along with André Linde and others, have argued this represents a serious internal problem for that particular model, since it would statistically predict that any given observer should overwhelmingly expect to be a spontaneously generated Boltzmann brane rather than an observer with a genuine evolutionary history, a conclusion sharply at odds with our actual experience and requiring, at minimum, that any successful multiverse model needs to be constructed carefully enough to avoid this bizarre statistical trap. This remains a genuinely unresolved, actively debated theoretical puzzle within the small community of physicists working on the mathematical foundations of eternal inflation. And it illustrates just how strange and still incomplete our understanding of these ideas truly is, even among the theorists who take them most seriously. Where does the research stand as of now in 2026? The picture continues to sharpen incrementally rather than resolve dramatically. Newer, deeper galaxy surveys, including expanded data releases from the Dark Energy Spectroscopic Instrument, an instrument mounted on the Mayol telescope in Arizona, capable of measuring the precise distances to tens of millions of galaxies, and continuing analysis of dark energy survey data, have refined our map of the Eridanus Supervoid's exact size, depth, and galaxy density with steadily improving precision, allowing increasingly careful calculations of exactly how much of the cold spot's temperature deficit conventional integrated Sachs-Wolfe and Rees-Sciama physics can account for. The consensus among most working cosmologists remains that a combination of the real supervoid and an accepted allowance for statistical chance, the universe simply being large enough that an unlikely but not impossible cold fluctuation eventually shows up somewhere, is the most probable, least exotic explanation, even if it does not yet feel fully, comfortably complete. Searches for the sharp bubble collision signature continue with each new generation of cosmic microwave background data. Ground-based instruments, including the Atacama Cosmology Telescope in Chile, have continued refining measurements of the cosmic microwave background at high resolution, while its successor projects and complementary efforts push toward even greater sensitivity. The Simons Observatory, a major ground-based cosmic microwave background experiment being constructed in the high Atacama Desert, has begun collecting data with substantially improved sensitivity to both temperature and polarization compared to earlier instruments, specifically designed in part to test exactly the kinds of large-angle anomalies, including bubble collision signatures that remain unresolved. Looking further ahead, the CMB-S4 project, a major coordinated effort involving multiple ground-based telescope arrays in both Chile and at the South Pole, is being developed as one of the most sensitive cosmic microwave background experiments ever conceived, with science operations anticipated to substantially ramp up before the end of this decade. In parallel, the Japanese-led Lightbird satellite mission, developed in partnership with international collaborators including NASA, is being designed specifically to map the polarization of the cosmic microwave background across the full sky, with a sensitivity that ground-based telescopes, limited by the need to observe through Earth's atmosphere, cannot match with a launch currently planned for later this decade. Any of these instruments, if a genuine bubble collision signature exists anywhere on the sky at a strength consistent with current theoretical predictions, should be sensitive enough to detect it clearly or, just as importantly for the progress of science, to rule the cleanest versions of the hypothesis out to a much higher confidence level than currently possible. On the Galaxy Survey side, the Vera C. Rubin Observatory in Chile, which began its main scientific survey operations recently after years of construction, is expected to produce an extraordinarily detailed three-dimensional map of billions of galaxies across a large fraction of the observable sky over the coming decade, further refining our understanding of the true size, shape, and density of the Eridanus Supervoid, and potentially settling with much greater statistical confidence than currently available exactly how much of the cold spot it can and cannot explain through conventional physics alone. The European Space Agency's Euclid mission, launched in 2023 and now in the midst of its primary survey operations, is contributing complementary data toward the same goal, mapping the distribution of galaxies and dark matter across billions of light years with a precision specifically designed to test subtle cosmological effects exactly like the integrated Sachs-Wolfe effect. It is worth noting, too, that the cold spot is not the only place where our best cosmological model has recently come under renewed pressure from new data, and mentioning this broader context helps place the cold spot's significance in perspective, neither exaggerating it as singular proof of anything, nor dismissing it as an isolated curiosity unconnected to the rest of cosmology. Since beginning science operations in July of 2022, the James Webb Space Telescope has repeatedly detected surprisingly bright, surprisingly massive galaxies at extremely high redshifts, corresponding to a time only a few 100 million years after the Big Bang, galaxies that appear, in a number of published analyses, to have grown larger and more massive faster than standard models of galaxy formation within the lambda cold dark matter framework comfortably predict. This has become known informally among astronomers as the early galaxy problem, or sometimes the impossible early galaxy problem, though that framing likely overstates the current tension, since several proposed refinements within standard physics, including more efficient early star formation than previously modeled, or systematic uncertainties in how the mass of these extremely distant galaxies is estimated from limited data, may substantially or entirely resolve the discrepancy as more data accumulates. A minority of researchers have proposed more significant modifications to standard cosmology to explain the tension, though, as with the cold spot, these remain contested, unconfirmed proposals rather than established alternatives. A separate, longer-standing, and statistically much more robust puzzle, called the Hubble tension, concerns a persistent, now high-confidence discrepancy between two different methods of measuring the current expansion rate of the universe, one based on the cosmic microwave background and the standard cosmological model, the other based on direct distance measurements to relatively nearby stars and supernovae, a discrepancy that has grown more, not less, significant as measurement precision has improved over the past decade, and which many cosmologists now consider one of the most important open problems in the field, potentially pointing towards some genuine incompleteness in the standard cosmological model. Though its exact resolution, like the cold spots, remains unknown. None of these puzzles, including the cold spot, currently rises to the level of overturning the standard cosmological model, which continues to successfully explain an enormous range of independent observations. From the detailed pattern of cosmic microwave background, fluctuations to the abundance of light elements, produced in the first few minutes after the Big Bang, to the large-scaled distribution of galaxies mapped across billions of light years. But taken together, these open tensions are a healthy reminder that even our most successful scientific models are provisional, continuously tested, and that the honest state of a field as active as modern cosmology is rarely a story of settled certainty on every front, but rather a story of a well-established core framework surrounded by a genuinely active, unresolved frontier, exactly where the cold spot sits. Stepping back from the cold spot specifically, the broader question it sits inside, whether we live in one universe or a vast, perhaps infinite ensemble of them, remains one of the most genuinely open and philosophically loaded questions at the frontier of physics. None of this is settled. That is, in the end, the most honest and perhaps the most genuinely exciting thing that can be said about it. The cold spot remains exactly what it was when Pablo Vielva and his colleagues first noticed it, in that Wilkinson microwave anisotropy probe data, a real, still not fully explained anomaly sitting in the oldest light we can observe, a stubborn discrepancy between what our best theories predict and what our best instruments actually see. Whether it eventually resolves into something comparatively mundane, a very large but ordinary void combined with an unlucky roll of cosmic dice, or whether future instruments somehow find the sharp, specific fingerprint that a handful of physicists have spent 2 decades searching for, evidence that our observable universe is not alone, that its edge, or something like it, was once close enough to touch something else, is a question current data cannot yet answer with confidence in either direction. What can be said with confidence is this: the tools to keep investigating are getting dramatically better across every relevant front at once. From cosmic microwave background, polarization measurements sensitive enough to catch a genuine bubble collision signature if one is really there, to galaxy surveys precise enough to finally settle exactly how large and how empty the Eridanus Supervoid truly is, to continued theoretical work sharpening or, just as valuably, ruling out the specific, falsifiable predictions that separate serious multiverse physics from untestable speculation. The theoretical frameworks that first predicted a multiverse might exist at all, eternal inflation, the string landscape, and the entirely independent ekpyrotic and cyclic brane collision models, continue to be tested, refined, and in some cases directly challenged by physicists working to determine whether they represent a genuine description of a larger reality beyond our observable horizon, or an elegant piece of mathematics that, however beautiful, may simply lie beyond what any experiment could ever confirm or deny, a distinction that matters enormously, and one that the physicists working closest to this problem take more seriously, not less. The further their calculations push them toward genuinely extraordinary conclusions. It is worth sitting with why a single cold patch of ancient light, barely a fraction of a degree cooler than its surroundings, has managed to occupy some of the most capable scientific minds and some of the most expensive scientific instruments ever built for more than 2 decades running. Part of the answer is simply that it sits at the intersection of several of the biggest open questions in physics at once: the true nature of dark energy, the ultimate fate and structure of cosmic inflation, whether string theory describes anything real about our universe, and whether the tools of quantum mechanics, so thoroughly confirmed in laboratories on Earth, can meaningfully be extended to describe the relationship between entire universes. A definitive answer to what is happening in the direction of Eridanus would not just resolve one anomaly, it would provide a genuine hard constraint on some of the largest, most abstract theoretical structures physicists have ever proposed. The kind of concrete empirical foothold that theoretical cosmology, working as it often does at scales and energies far beyond anything a laboratory on Earth could ever directly probe, urgently needs and only rarely gets. The other part of the answer is more human than technical. Every civilization that has looked up at the night sky has asked some version of the same question, whether what we see represents the whole of existence, or only the visible portion of something larger. For most of human history, that question belonged entirely to philosophy and religion, unanswerable by any method available at the time. It is a genuinely remarkable feature of the present scientific moment that the question has, for the first time, developed a testable edge, that a specific, mundane-sounding measurement, the precise temperature and polarization pattern of microwave light arriving from a patch of sky in the southern constellation Eridanus, could, in principle, bear on whether our universe is singular or one among many. That the current data cannot yet settle the question is not a failure of the science. It is simply an accurate description of where the frontier presently sits, and frontiers, by definition, are where the next real discovery, whatever it eventually turns out to be, is most likely to be found. Somewhere in the constellation Eridanus, a patch of the oldest light in existence continues to run just slightly colder than physics currently. Comfortably, explains. For now, that is where the story has to end, not with an answer, but with one of the most carefully guarded, genuinely open questions in modern cosmology, still waiting, patiently, for better data, better instruments, and perhaps a little more time before the universe finally decides to tell us exactly what we are looking at.